Hello everyone. So this video I am going to discuss Mitsunobu reactions, its important features, mechanism and also some examples. So what is Mitsunobu reaction? As you can see here, we have taken 1 degree or 2 degree alcohol and stereochemistry is also mentioned here because we will get the product with inversion of stereochemistry. And here we have taken the reagent which is acidic compound and it is drawn in this way, that is H and Nu, because Nu will be generated from this HNu, that is a nucleophile. And the other reagents are dead, that is diethyl azo dicarboxylate, and we have taken triphenyl phosphine. So in combination of these reagents, from this substrate we will get this OH is now replaced by Nu and obviously with inversion. So this is a substitution of 1 degree or 2 degree alcohol, that is a OH group substitution, and with inversion. And now depending on the nature of Nu, we can have different types of substituted product. So what are the important features? The principle of the reaction is to convert OH group into a good living group. So that is why we have taken this type of reagent combination, because OH itself is not very good living group. Okay. So now after it is converted to good living group, it will react with variety of nucleophiles and that depends on nature of this Nu, and this is involving SN2 mechanism. The nucleophile employed should be acidic. Okay, this is very important feature because the reagent dead, there should be some protonation and that we will see in the mechanism obviously. Now because of this, that is it must be protonated and that proton will come from HNU. That is the reason it should be acidic in nature. And this will happen during the course of the reaction and it is necessary so that we can avoid some side reaction. Fine. The main advantage of this reaction is that this is one pot synthesis, so we can mix everything together and we can get directly the product. This reaction is somewhat similar to apple reaction. Now apple reaction, one video I have already uploaded. You can click on the link right on the screen. I will also add the link in the description box. Kindly check there. Now we will see the mechanism, what is happening here. The first step is attack of this PPH3 triphenyl phosphine on DEAT, that is diethyl azo dicarboxylate. So once this is happening, suppose it is attacking here, now this double bond is broken, negative charge is over the second nitrogen and phosphorus will be now positively charged. So this is Zwitter ionic intermediate because within the same molecule you have positive charge as well as negative charge. What is happening in the second stage? This intermediate now, it will deprotonate the acidic compound. So this H, now it will be taken by this negative charge. So now, sorry, there is one positive charge. Now this is NH and the negative charge, initially it was on N, now it is on the nucleophile. And this is, I have already mentioned previous slide that this, that is HNU, it must be acidic, otherwise there will be some side reaction, and that side reaction is that instead of this nucleophile which is generated from HNU, what will happen? This compound will act as if the nucleophile, but that is not expected. So that is why here this step is very important, because if the concentration of this species is very high, instead of Nu minus, it will react with the substrate and that we have to avoid. So that is why this N minus must be attached with this H, and now we have already generated the nucleophile, that is Nu minus. This is the second step. The third step is the phosphonium intermediate binds to alcohol oxygen. So alcohol oxygen, there is lone pair over oxygen. It will attack this phosphorus and PN bond will be broken. So this bond is broken. You can consider this H, it is now as if over this nitrogen. So we are getting this type of OPPH3 bond. Positive charge is still present. And in the final stage, the nucleophile, which is already generated in the second step, that will perform a SN2 attack. So it will attack from the opposite side, and that is why you can see here inversion of configuration is taking place, and this is a final substituted product. So when nucleophile is attacking from the opposite side and this oxygen carbon bond is broken, what will happen? It will be O minus and PPH3 plus. You can also write the structure as if it is, sorry, it is O double bond PPH3. Now this will be the side product, and here actually the side product, that is the formation of strong P double bond O, which you can see in the side product, that is the driving force for this reaction. Because when you have some side product, and in that side product there is some strong bond, obviously it will help to shift the equilibrium from left hand side to right hand side. So that is why it is the driving force for this reaction. Now what are the probable acidic compounds? I have mentioned it as I have mentioned it as it is HNU, but what is this HNU? What is the nature of this? That we have to know. So HNU having pK less than 50. This HNU, it should be such that pK value must be lesser than 15, and it is better if it is lesser than 11. So this should be the criteria. Now the first possibility is it can be a carboxylic acid. So if it is a carboxylic acid, that is RCO2H. So this part is Nu and this is H. That means if your substrate is, you have chosen where you have two different R groups, then in place of OH, I am just neglecting the stereochemistry to make it simple. So it will be now OCOR. So when you have taken carboxylic acid as the HNU, you will end up with ester. And if you want this ester group to convert to alcohol, then you can do hydrolysis. But you will get again another OH group, but that will be with inversion of stereochemistry. So that is an important application. Then you can take some alcohol, you can take aromatic alcohol, you can take thiol. That means now the product nature will be something like this. That is, if your alcohol is ROH, the product should be like this. I am putting here double prime so that all the R groups are different. Or it may be that aromatic alcohol, it may be OPH, it may be O. It may be SR. So thioether or ether, this type of product we can get if we are starting with this type of HNU substrate. Then N heterocycle, that means suppose we have NH and there is some ring type of structure. Now in this case, the product that we are going to get, it will be N and then R prime. So see how many different types of product we can get, thus changing the nature of HNU, and each time there will be inversion of stereochemistry. Amide or amide like NH. Now here suppose you have started with thalamide. Now thalamide is this molecule, C double bond O and then NH. Now if you have started with this type of compound, the product that you get is N, 5-membered ring, double bond O, double bond O. Okay. Now from this, when we do further Gabriel synthesis, what we get, this group, now it will be converted to NH2. So in this way, further reactions also you can do if you want to make, finally if you want the substitution as NH2. So Gabriel synthesis also we can do if we have taken this type of HNU. Then hydrozoic acid, if we take N3H, then the product will be like this, some azide group will be there. Now we can do Storinger reaction, and as a result again we will end up with this type of amine. Okay. So here we have taken all the variety of probable acidic compounds that we can take, and one more acidic compound also you can take where active methylene group is present. Acid methylene means there will be some CH2 group, and both sides if you have some electron withdrawing group, strong electron withdrawing group, then also this compound can act as HNU, or there may be one more group also, but one hydrogen must be present, right? Now we will see some examples from some research papers. So here we have alcohol and this is HNU, and this NU, it can be different types. You can see here some acid is there, AROH is there, and final compound will be depending on what type of NUH we have taken. So instead of dead, here a slightly different structure is there, but it is also having some similarity with the reagent date, right? And PPHD also present. Then we have taken this type of HNU, and this is the alcohol, and we are getting substituted product. Instead of dead, now it is DIAD, which is diisopropyl azo-dicarboxylate. That is just ethyl group is replaced by isopropyl group. That is the only difference. Then we have one more example here. This is the alcohol, and see DMEAD. Now this is also just like a dead type of reagent, and this is our HNU where this is nothing but carboxylic acid, and we are getting OH again. So, but see, it is inversion of configuration. As I have said in the previous slide that OH group, when you are using some carboxylic acid, first you will get ester. But if you are doing hydrolysis, you can also convert it to OH. So you are starting from alcohol, you are also getting alcohol, but with inversion. So depending on our requirement, what we are we want to synthesize actually, according to that we have to choose the HNU, and further steps also we can do. As you have seen, we have done Gabriel synthesis, Schrodinger reaction. So everything depends on what we actually want to prepare. So that's all about this video. Okay, thank you for your precious time.